Okay, 13.4, this is our last section of chapter 13, and this is all about nonlinear inequalities. So we have two things to talk about in this section. The first is how to graph nonlinear inequalities. Nonlinear inequalities. And the second is graphing systems of nonlinear inequalities. Systems of nonlinear inequalities. So there's a couple changes to our linear inequalities that we're going to talk about. Now, I think it's easier just to show these things and make note of them as we work through a problem or two than to write it out in a list so you have some context. So let's start with this problem. We're going to graph x squared over 9 plus y squared over 16 is less than or equal to 1. So the first thing that we have to be able to do is graph the associated equation. So if we start a little list here, we need to graph the associated equation. And for us, that's x squared over 9 plus y squared over 16 equals 1. Now they're both positive and equal to 1, so this is an ellipse. Ellipse is a P, not a B. And since the denominator on the y is the larger number, the y-axis is the major axis. And we know that it's just x squared and y squared, so the center is 0, 0. And then we go out square root of 16 and square root of 3 in the x and the y direction. So our points, our vertices, so to speak, are 3, 0, negative 3, 0, 4, 0, and negative 4, 0. So here's where something new comes in before we graph. We have all the things we need to graph coming from section 13.1, is we need to look at the inequality symbol. If it's less than or equal to or greater than or equal to, then we have a solid graph, solid line. If it's just less than or greater than, we have a dashed line on our graph. So we did talk about this when we did linear inequalities, but make sure you box that up or make note of it somehow in your notes because this is important. So for us, we have less than or equal to, so we're going to have a solid ellipse. So now when I go to sketch my graph, now here's the thing about these inequalities, is they don't need to be perfect because what we're looking at is their inequality, so we're going to be shading a region. So I know I need to go 1, 2, 3, 1, 2, 3, this is negative, 1, 2, 3, 4, 1, 2, 3, 4, negative 4. I have this point, this point, this point, and this point. And I draw my ellipse as best as possible. Mine looks pretty circular, but not a big deal. Label your points. 3, 0, 0, negative 4, negative 3, 0, and 0, 4. So whoever's looking at it understands. You have a solid line because of the inequality symbol. And then the next step, this is where the biggest change comes from. Our linear inequality, so this is 2, this is where we shade our region. And this is the solution region. So for linear equations, we always thought of lines. You can be above or you can be below. For conics, less than or equal to, it's not above and below, it's inside. And for greater than or equal to, it's not above, it's outside. So again, box this up, mark it off somewhere in your notes to make it obvious. This is the difference. So when we go to shade this ellipse in, we look at our inequality symbol, and that tells us where we shade, inside or outside. Now we have less than or equal to, so we're shading inside. So then when we go to shade, we shade inside like that. And then this is x squared over 9 plus y squared over 16 is less than or equal to 1. So any point that you pick that's inside or on the ellipse will satisfy this inequality. And you can pick one. Let's pick an easy one. Let's do 1, 0. Well, 1, 0 makes this 1 over 9 plus 0, and is 1/9 less than or equal to 1? Yeah. Let's pick something like 2, 0, or 0, 2. So that makes this x term go to 0. Y becomes 4 over 16. 4 over 16 is less than 1. So you can always double check where you're supposed to shade. And if you're ever not sure, pick a point inside or outside and test it. Because if it works once here, it's going to work everywhere inside. That's how inequalities work. They're not going to change based on the problem, based on the point. So let's take a look at another example then. Let's graph the inequality. 4y squared is greater than x squared plus 16. So the first thing that we want to do is put this in standard form. So I'm going to move the x squared over. 4y squared minus x squared is greater than 16. And I'm going to divide everything by 16 to get y squared over 4 minus x squared over 16 is greater than 1. So now we can look at this and start to identify the conic. So since this is a negative, this is a hyperbola. A is equal to 4. Remember, A always comes from the x. B is equal to 2. And the x term is negative. So x term being negative means that we open on the x or on the y-axis. So now, since we're not graphing the conics, we don't need to be perfect. We know that since b is 2, we're going to have 1, our center. Since it's just y squared and x squared is going to be 0, 0. And our points, our vertices, since it's opening on the y-axis, will be at 2, 0 and negative 2, 0. Now we don't need to get perfect with this, again, because we're doing an inequality. So if you want more practice, this is a great section to practice your conic graphing. I'll go up 1, 2, 1, 2. Go by 2's here, 2, 4, 6. This is -2, this is +2. This is -2, -4, -6. So we know we have this point and this point. We know that we're opening up on the y-axis, so our hyperbola is going to look something like this. Is that perfectly what it's going to be? Probably not. But again, we're not looking to be perfect. So one thing that I should have done is I should have looked at my inequality. This should be dashed because it's only greater than. It's not greater than or equal to. So I'm going to go over this in a darker pen, try and make the dashes appear. So it doesn't look terrible. So it should be dashed. Again, it's because it's just greater than. It's not greater than or equal to. So if you're like me and you forget that sometimes, and you're doing this in pencil, you just erase a little bit to make it dashed. In fact, I would honestly recommend that you always do your inequalities in pencil, not in pen like me. If you do it in pen, you have two options. You can either get a darker, thicker pen and go over it to show that it's dashed, or write a little note here that says dashed line. I shouldn't say or, you should be doing both. So try and dash it or redo it. Again though, you should do these in pencil. It'll just save you some headaches. So now we're looking at a greater than. And I said in the last example, we look inside or outside. Well, inside the hyperbola is in between the points, and outside the hyperbola is above and below. So if you're ever not sure, just pick, like I said, pick one point to check. So pick 0, 0. Looking at our inequality, is 0 greater than 1? So if we have 0, 0 as a point, 0 minus 0 greater than 1, this is false. So that means 0, 0 is not in the solution region. So our shading should be above and below. So now what we want to do is look at systems of inequalities. So we'll start with a simpler one. So we're going to graph the system, and our system will be x less than or equal to 1 minus 2y, and y less than or equal to x squared. So the first step we want to do when we're graphing nonlinear systems is switch everything to standard form. So that, just like we did with the hyperbola in the last example, write it in standard form, and each conic gets its own standard form. So parabolas, circles, hyperbolas. We also can have lines. So this is a line, and this is a parabola. So what we want to do is write this line in standard form, y something. So rewriting the y less than or equal to x squared, that's fine, because we usually have y equals x squared for parabolas. So I need to solve this equation for y, which would be y is less than or equal to, so I subtract 1 over, x minus 1, divide by -2, which is why this symbol flips. So this becomes negative x plus 1 over 2. Or y is less than or equal to -1/2 x plus 1/2. And y is less than or equal to x squared. So then you graph each inequality separately, but on the same axes. So that's going through what we just did, graphing the associated equation, and then graphing the solution region by shading inside or outside, or for lines, we still do above and below. So for this problem, they're both less than or equal to, so both are going to have solid lines. Now I like writing this, again, like you saw in the last example, I didn't write this and I drew it as a solid line, which should have been a dashed line. So if you're like me and you forget that sometimes, I'd recommend getting into the habit of writing it just like this at the start so you know what you're doing. So we go to graph this. So our two equations, y equals x squared and y equals -1/2 x plus 1/2. So I'm going to have 1, 2, 3, 2, 1, 2. Guess we can extend that a little bit. So scale this by 2s, 2, -2, and then 2, +4. So I'm just going to start with graphing y equals x squared. 0, 0, 1, 1, -1, 1, 2, 4, -2, 4. We have our nice parabola here. And then we graph the line. So the line has y-intercept of 1/2, which goes through right here. And then it has a slope of -1 over 2, so down 1 over 2. So we're going to go down 1 and over 2, which would put us at, if this is -1, -2 here, down 1 would be -1/2, over 2 would be 2, -1/2, so that's going to be right there. And we're going to connect that line. So now is where I like to use 2 different colors. You can also do 2 different directions in how you shade. So I'll show both of those. So starting with the line is less than, so that means we're below the line. So our line shading would be this. Everything below the line. And then the quadratic is also less than, so that means outside the quadratic. Now outside the quadratic, again, is outside. And if you're ever not sure, just pick a point. So pick a point like 1 or 0, 1. That's clearly on this side of the quadratic. 0, 1, when you plug in, is 1 less than or equal to 0? The answer is no. So that means you're not shading here, you're shading out here. And so the shading for the quadratic, this is what I mean by different directions here, is this. Make that a little obvious in there. And so what people typically do at this point is your solution is only the overlap. So notice the line inside here is shaded in this region, but outside the quadratic is not. So we need to make this more obvious. Now the two colors in two different directions help, but if you're still not sure that it's quite obvious, a lot of people will do a diagonal shade to show exactly where the solution set is. And it is a little time consuming if you drew big axes like I did. But now there's no question that there is some gap here. And so you just make a little key off to the side. And just following how you shaded it, this is the solution set for y less than or equal to negative 1/2 x plus 1/2 and y less than or equal to x squared. Now, when you're doing this on the computer in my math lab, that's not going to be an issue because they're not going to have the extra shadings. Most of these, I believe, are choices, multiple choice, where you pick the correct shading. So this is just for you when you're doing it on paper to make sure you understand where the solution is and where it isn't. Okay, so that's one with a line. Let's take a look at the harder version to finish this up when we have two different conics in our system. So we are going to graph the system. And our system will be x squared minus y squared is greater than 36. This is actually should be 4x squared minus 9y squared is greater than 36. And 4x squared plus y squared is less than 4. So step 1, write these things in standard form. We have a minus here, and we have a, so that tells me that this is probably a hyperbola. Since we have both pluses here and this number here and this number is not the same, this is probably an ellipse. And I say probably because until you put them into standard form, you can't be sure. So standard form for ellipse and hyperbolas both have 1s over here, so I'm going to divide this first equation by 36. And we get x squared over 9 minus y squared over 4 is greater than 1. And dividing this whole equation by 4, we get x squared plus y squared over 4 is less than 1. So it is definitely a hyperbola and an ellipse. So we start with graphing each one. So thinking about the hyperbola, number 1, it should be dashed because it's only greater than. It opens, since the negative is on the y, it's going to open on the x. And those vertices then are going to be at the square root of 9, which is 3, 0, and negative 3, 0. For the ellipse, it's again dashed, since it's only less than. And it has center at 0, 0. Since it's just x squared and y squared. And our vertices, you can think of this x squared as over 1. So this is at 1, 0, negative 1, 0. Square root of 4 is 2, 0, 0, 2, that's the y term, and 0, negative 2. So now we can start to graph these. So we need 1, 2, 3, we'll go to 4. We need 1, 2, 3, 4. We'll go to 5 just for fun. -2, -4. 1, 2, 3, 4. 1, 2, 3, 4. We'll go to 5 here. So let's start with the ellipse just because. So center at 0, 0, points 1, 0, -1, 0, 0, 2, 0, -2. It's a dashed line. So I'm going to make my ellipse dashed as best I can. How about this? Let's do it in black. It'll make it more obvious. That looks pretty dashed. And for the hyperbola, we are opening on the x-axis at 3, 0 and -3, 0. So here's 3, 0, here's -3, 0. Again, we're not trying to be perfect, so we're not going to do the box method. We're not going to do the asymptotes. And it's also dashed, so it's going to open something like this. And something like this. So now we can do our shading. So the hyperbola is greater than, which means outside. Remember, outside hyperbola means outside of the edges. So that would be here, like this. And here. And then the ellipse is less than. So that means inside, which would look like this. Now remember, our solution is the overlap. So these two regions and this region never overlap, which means that there is no solution. No solution. Just like there can be no solution to the systems of equations, they may not intersect. If they don't intersect or they don't have the right inequality symbols, then there would be no solution. Now, if we changed one of these, we would have a solution. So don't think that this is going to happen every time you have an ellipse or a circle with a hyperbola. So if this was inside instead of outside, we'd be shading here in between the hyperbola, and then our solution would be strictly inside the ellipse. Similarly, if we change the ellipse to the greater than and make it outside, we'd be shading all outside of the ellipse, and that would make these two regions our solutions as well. So keep that in mind as you work through these problems. But that is the end of chapter 13. Well, that's the end of section 13.4, and with it, chapter 13.